Welcome to Design of Concrete Structure Code. So this is lecture number 16. Here we'll be discussing a problem or how to design a short axially loaded compression member or column. So in the lecture number 15 we have started a new topic, that is how to design the compression members. So we have seen what is compression member. When a member is subjected to compression force, then we call it is a compression member. So typically column in a structure is a compression member because in a column forces are actually acting in a compression manner. So based on the loading pattern or how the loads are applied on a member, we can classify it either it is a beam or it is a column. So if a load is acting transversely about the axis of this member, if any load is acting perpendicular to the axis, then we call it this is a beam. Okay, so although both the members are vertical in nature, both are vertical, but still this is a beam because here loads are applied in a transverse direction, whereas in this figure it is a column because here the loads are acting in a compression manner. So in the last class we have discussed the different classifications of columns also. So we have seen typically there are three types of columns. One is pedestal, and then we call it column based on the uh, dimension of the member. We can classify it either pedestal or column, or it is a wall. So again, based on the loading pattern also we have seen there are three types of columns. One is axially loaded column. If the load is acting axially to the column, then we call it the axially loaded column. And if the load is acting in a eccentrically about one axis, then we call it the uniaxial bending column. And when even the eccentricity is about both the axes, x and y, both the axes, then we call it is uh, biaxial bending column. So in this lecture we'll be discussing a short axially loaded compression member, how to design the short axially loaded compression member. So again, we have discussed in last class also, there are two types of column, that is short column and long column, that is based on the length of the column. Okay, so if length of the column is very high, in that case the failure of the column will be happening because of buckling, not because of crushing of material. Whereas if the length of the column is very short, then the failure of the column will be happening because of crushing of material, not because of buckling. So uh, based on this length or based on the slenderness ratio, we can classify a column into two parts. One is short column and another is long column. If the slenderness ratio is more than 12, then we call it is a a long column. If the slenderness ratio is less than 12, then we call it is a short column. So let's get started. So to design a short column, so please remember in this example we are designing a short column, and again the forces are constant axially applied. So it is first case of loading pattern, that is where the loads are applied only axially. So let's draw a column, short column here. So this is a column, and if you see the diamond, if you see the plan view will be something like that, and the loads will be acting at the center of this, or the CG of the column. So that is our short column, and if the load is acting just at this point, middle point, then we call it is a axially loaded column, right? But we have seen in the last lecture also, it is very difficult to construct a building and construct a column where the loads are acting just at the axis, just at the axis point loads are acting. So it is very difficult, we can't make practically all the columns will have some amount of eccentricity. So whatever it may be, small or large, but always there will be some amount of eccentricity. So that's why our code has specified that even in case of axially loaded column, we should consider a minimum area or the minimum eccentricity. So that code has specified if it is 5% area here. So although if load is acting in this area, in this region is actually 5% of B and 5% of D. Okay, this entire length B and this is D. So 5% of B is this one, 5% of D is this one. So even if the load is applied in this region, then also we will consider that this is a axially loaded column. Although in reality, because even if load is applied here, there will be small eccentricity, right? But code said that even that eccentricity we can't ignore. Always there will be some eccentricity. So let's better to use a area here. 5% area we have considered. In this area, if loads are applied, then also we will consider it. It is a axially loaded column. So how we got 5% value? So this length is basically 0.05 b, and this one is 0.05 d, right? So total 5% area. So this 5% came from the concept of short column. So in short column, what is short column? So in short column, basically if the slenderness ratio is L effective by D or B, which one is least lateral dimension, should be equal to less than, this value should be less than or equal to 12. If this condition satisfies, then only we call it, this is a short column, right? Center ratio should be less than or equal to 12. So from here you can find it out. L effective is nothing but 12D. So our code has specified the minimum eccentricity formula also. L effective by 500 plus, we have discussed in the last class. So in that, if you substitute L effective is equal to 12D, and then if you compute, you will find that this length, eccentricity length, is basically 0.05D, means 5% of the total D, and here also it will be 5% of the B. So that's how we can say that even if the load is applied in this rectangular area, 5% area, then also we'll consider our column is subjected to axially loaded. So now we understood which and we can find it out whether a beam is axially loaded or uniaxially bend loaded or biaxially loaded. So now let's determine the governing equation for the column design. So if you visit the clause number 39.3 IS 456, you will find this formula. So what is this formula? This is PU equal to 0.4 FCKAC plus 0.67 FYAC. What is PU? PU is the factored axial load on a member. So how much maximum compressive load a compressive member can take, that is PU. What is FCK? Characteristics of concrete length. ASC is area of concrete. FY is characteristics of steel reinforcement, and ASC is the area of longitudinal reinforcement for the column, right? So let's understand here how this equation arrived, how this point is 0.4 and how we got 0.67 FYAC. What is the fundamental things? So as I mentioned here, so this is a column you can consider, and the load is acting here, compression load is acting, and the value is pu, right? And this is a cross section, as I mentioned. So cross section, this area is small b and this is capital D. So this one is b and this dimension is capital D. Okay, and the total load is applied, for example P. So you have increased gradually the load P, and after some extent you will find there will be cracks in the in the column member. So this failure will be happening because of crushing of material, not because of buckling, because we considered it as a short column, means length is low. So if you apply a compression load gradually, if you increase it, after a certain point the column will fail, the material will crush at the center or anywhere. So in because of that, so this failure load, let's consider it is a pu. Pu means that maximum load compressive force this member or this column can take, and this is a cross section of this member. Let's consider it as a rectangular section with B and capital D is the area. So now how much load it can take? Now that is the question, right? So total pu is the total load it has taken. So this concrete is actually made up of, you know, concrete as well as steel, right? This column is made up of concrete as well as steel, so two materials are used, right? So you have if you consider four reinforcements are there in the four corners. Okay, so let's consider this is just example I am giving here. So now the whatever load is applied pu, that pu load will be taken care by these four reinforcements as well as the concrete itself. Okay, so both concrete will take some load and steel member also will take some amount of load. So now how much concrete will take it and how much steel will take it? So if you recall, in the last lecture we have discussed about the assumptions of compressive member design. So in that our IS code 456 said the maximum strain, failure strain in a concrete in compression is 0.002. If you recall, so that is our code said failure strain is 0.002. Okay, if you just remember this, we discussed in last class also. Concrete fails, so concrete fails, compression failure. Okay, so this is compression failure is 0.002. So now, so when the strain reaches, so what happens? We are applying the force P gradually from 0 to gradually we are increasing the load. So because of that, the when the strain level initially it was 0 and then gradually if you are increasing the load P, the strain level also reaches from 0 to 0.001, and when the strain level reaches to 0.002, then the concrete fails at the center or anywhere in the column, and ultimately the failure of column will be happening. So the failure strain is 0.002, that we understood now. Okay, so concrete when reaches to 0.002 material will fail. Similarly, steel also, maximum capacity of steel, I mean strain level in a steel also is 0.002. Okay, although steel can take more strain, but anyway both are casted monolithically. So when if concrete fails, then only we will call this column has failed, and the failure strain is 0.002. So now, if you recall the stress strain diagram of concrete, we have discussed in the earlier beam classes, at the beginning classes. So stress strain curve of concrete will be something like that, if you recall. So that was up to 0.002%, it is linear, and then you have the straight person 0.0035, and this value is 0.44 FCK, right? And this is the strain level, we have discussed it. So this is your strain axis epsilon axis, and this is the stress axis sigma. So this is the stress strain curve of concrete we have discussed. Now you remember, I hope, how we got 0.446 FCK. So basically this is that FCK divided by partial safety factor 1.5, again divided by 1.5 is the size factor or the shape factor. So you get basically 0.44 FCK. So this is the diagram we considered. So here what is the failure strain in concrete? So failure strain in concrete is 0.002. So 0.002 correspondingly, what is the value? Value is 0.446 FCK, right? So the stresses on a concrete is 0.44 FCK, right? So but what we considered here, we considered even if the load is acting in this area, small area, then also we'll consider it is a axially loaded member, right? But in reality, you will have always some eccentricity in a member. So because eccentricity is there, that's why the strength of concrete also will be reduced, because because of eccentricity the additional bending moment will be developed into the structure, and because of the strength of the material will be reduced. So quote said, even if if load is acting in this small area, 5% area, then also you consider it is a axially loaded member. So now because of this we are our consideration of 5% area, right? The strength of the concrete is reduced actually, because load is not exactly acting axially, but it will have some eccentricity. So that's why whatever values we got it, we should reduce this value by 10% approximately to get the actual stresses in a concrete. So if you reduce this value by 10%, what you will get? So 0.44 into 0.1, if you multiply it, you will get something 10%. You have to reduce it, so it will be 0.44 into 0.9, 0.9. So 0.1% we have reduced, so this value will comes out to be 0.4. So now the strength here, strength of the concrete is actually 0.4 FCK, not 0.446 FCK. So this is the stress in a concrete into area of concrete. So area of concrete is ASC. So that's what the formula here is. PU equal to 0.4. 0.4 we got it from here. 0.4 is the stress level in a concrete. 0.4 FCK multiplied by ASC is the area of concrete, plus Again, in the steel also will take, right? So this 4 steel or whatever number of steels we provide, steel also will take some amount of load. So how much steel will take? So steel's failure is happening, right? So 0.87, if you recall, stress strain diagram of steel, so something like that. So stress strain diagram of steel, we considered it something like that, and that was 0.87 Fy, right? Maximum value. So that 0.87 Fy is corresponding to, maximum strain, whereas here the strain level at which the compression member will fail is 0.002. So somewhere here. So if you interpolate corresponding to 0.002 strain level, what is the stress at the steel, that is comes out to be, 0.67 Fy. So corresponding to 0.002 level steel, it will comes out to be 0.67 Fy for Fe 500 grade of steel, and for other Fe 415 and Fe 250, these values are little higher, maybe 0.71 and 0.69 something. But our code said always we should go with safer side, and we should use 0.67 Fy is the stresses on a steel multiplied by the area of area of steel in column AC. So area of longitudinal reinforcement for column ASC. So if you multiply stress into area, you will get the force. So this much force will be taken care by the steel, and this much force will be taken care by the concrete. So total, how much force Pu is applied, and Pu, that much will be concrete, and that much will be taken care by the steel. Okay, so this is the formula governing equation which we'll be using for the design column. So now ASC is what? ASC is the area of concrete, area of steel. That area of steel will be P into Ag. P is the percentage of concrete, percentage of steel in a column. P into Ag is the total gross area of the column by 100. We can write it ASC is in this form, and similarly ASC also we can write it in terms of Ag. Ag is the gross area, total area, which will be 1 minus percentage of steel. You will get simple calculation. You will get it ASC and AC in terms of Ag and P. Ag means total gross area, and P is the percentage of steel. So if you substitute ASC and Ag value here, so ultimately this is our final expression. You get it. Okay. So if you use helical reinforcement, then basically the Pu, whatever Pu value you get it, you have to increase this Pu value by 1.05 times. Why? Helical reinforcement means what? The reinforcements are provided. So in helical reinforcement, how the ties are provided, something like that, right? So like that way ties are provided. Anyway, you have the longitudinal bars also. So because of this continuity in the helical reinforcement, because of that, it will take little more load compared to normal tied column. So if you are using helical tie, then this value can be increased by 5%. That's why it is multiplied by 1.05 into the same value. So you will also get this expression in the IS code clause number. Here if you visit, you will find both the formulas. And now just now I explained also how this formula has derived from the basics. So these are the, so now let's get started by solving an example problem of short column. So what is the question here? Design a design the reinforcement in a column size. Column dimension is given B into D, right? B into D is given. B is always shorter dimension, so 400 is shorter. Cross sectional area is given to us, subjected to axial load. Axial load is also given, which is 2000 kilonewton, under the service load of live load and dead load, whatever is it. So 2000 kilonewton load is compression load is coming into our column, and the B and D value also given to us. Though the column has an unsupported length of 4 meter. So unsupported length means the total length of the column is given 4 meter, and effectively held in position and restrained against rotation in both the hands. Now here it is given that which type of support is there in a column. So it what is mentioned, it mentioned that effectively held in position. So we'll have a column, and total unsupported length is given. This is unsupported length, which is 4 meter is given to us, and how much total load is coming, that also given to us. So this load is 2000 kilonewton. Okay, this is not factored load, this is just a load acting 2000 kilonewton, and the cross sectional area also given to us, B and D value, which is 400, and D value is this one, which is 600. So all these values are given to us. And what is the support condition? Support is effectively held in position and restrained against rotation, right? Means effectively held in position means there is no translation in any direction. So that is effectively held in position and restrained against rotation. Rotation also restrained means the support, both the supports are actually fixed support because it is, rotation also restrained. So both the ends are fixed end. So that support condition also given to us. We have to use M25 and F415 grade of steel to design the column. Okay, so both the supports, both the ends are actually fixed end, that is given, and all these parameters are given. We have to find it out, the reinforcement and lateral reinforcement as well as the longitudinal reinforcement. So let's get started. So what is the first step? So step one is to check whether this column is short column or long column, because if whatever formula we have derived, that is only for the short column. So first compute what is whether the column given to us is short column or long column. So if it is long column, then the formula whatever we have derived, that is not applicable here. So given L is 4000, right? Unsupported length is given to us, which is 4000, and B is given to us is 400, and D is given to us 600, right? So and what is the support condition? Support condition means, so this is the column, right? And this is the column, and what is the support here? Both the sides supports are given to us fixed support, right? So fixed support. So fixed support means if you go to table 28 IS 456, there you will find the what is the value of K, right? K is effective length, L effective equal to K into L, right? So this K value we will get it in the table number 28. So table number 28 for the fixed end support case, the K value is given to as a 0.65. If you visit table 28, you will get for the fixed end support, if the both ends are fixed, then the K value is 0.65. So 0.65 into L, so L is 4000, so this will be 2600. So now effective length L effective is actually 2600. So L effective by D, so slenderness ratio we are computing. So length by dimension, least lateral dimension, L effective by D will give you 4.33, whereas L effective by about B axis will give you, divided by 400 will give you 6.5. So both the values are less than 12, right? So if so slenderness ratio is less than 12 means it is a short column. So it is proved now that it is a short column, right? Because slenderness ratio is less than 12. So now you understood. In step one, basically we are checking whether the column is short column or long column. So now we understood this is a short column because the slenderness ratio is less than 12. So step one completed. Now step two is minimum eccentricity. As I mentioned, all columns should have a minimum eccentricity, right? So Emax Emax is, so E mean actually Ex mean is greater of LEX by this formula we got it from IS 456, right? So if you compute it, so that you will get it 25.2 mm or 20 mm. So whichever is greater, that we have to consider it as the minimum eccentricity. So minimum eccentricity is how much? So minimum eccentricity is 25.2. Which one is greater? So this for value you got it 25.2 and 20. So obviously 25.2 is higher. So this is Ex mean, minimum eccentricity about x direction, and minimum eccentricity about y direction is just substitute this formula we got it from IS 456, and you get 20 mm. So in x direction you have minimum eccentricity of this much, and in y direction minimum eccentricity of this much. So now, as our code said, if this minimum eccentricity is within the 5% of this B and D, then also we'll consider it as axially loaded column, right? So in the second step, in the first step, if you recall, we find it out whether the column is short column and long column. But in the second step, we are finding out whether the column is axially loaded or uniaxially loaded or biaxially loaded, which type of category it is. So we computed minimum eccentricity about x-axis, and that is Ex. So if you see, this is the CG, and Ex value is 25, right? 25.2. Similarly, Ey value, we got it, Ey value is here, so this is 20. Okay, so now we have to find out whether this area is 5% of the total area or not. If 5% of B and 5% of D, if it is 5 in between 5% of B and D in this area, box area, then we'll consider it is actually loaded column, right? So that we are computing now. So Ex already we computed, which is 25.2, and Ey is 20. Now 5% of D is how much? That comes out to be 30. So total length is, total allowed is 30 mm, whereas ours is 25.2, right? So this point, eccentricity point, will be lying inside this triangle, inside this rectangle, right? So that's why it is a axially loaded column. So 0.5 b also comes out to be 20, right? So it is exactly inside this rectangle. Our point is this one, 25.2 and 20, which is inside this rectangle. That's why this is the axially loaded column. So this is also proved, hence the equation whatever we have derived it, that is applicable and we can use it also. So in the step 1 we checked whether it is a short column or not, and in the step 2 we have checked whether it is axially loaded column or not. By computing minimum eccentricity we computed based on these two formula, and that point we checked it is 5% area, of the CG, and then we concluded that this point is inside this rectangular portion, 5% area, and this is actually loaded member, and we can use the formula which we have derived in just 2 slides before. So now area of steel, very easily now we can compute it. So our load is given to us 2000 multiplied by 1.5, because partial threat vector we are using now 1.5. So 2000 into 1.5 is 3000 multiplied by 10 cube. We are converting kilonewton into meter Newton, and this formula we just plug in all the values, right? Pu is equal to 0.4 FCK ASC plus 0.67 FY ASC. So basically we are finding out ASC value. ASC value means the area of steel in compression, ASC value. So P value is this much, equal to 0.4 FCK. We are using FE, Fe415 and M25 grade of concrete. So M25 means 25 into AAC means area of concrete. So area of concrete will be how much? So total gross area minus area of steel, right? So what will be the area of concrete? So area of concrete will be how much? So total area is you have, and in the middle you have concrete, the steel also, right? So the area of concrete will be total gross area minus area of steel, right? Area of steel. So gross area is 400 into 600 minus area of steel ASC plus 0.67 FY is 415 and ASC. So from this quadratic expression you can get it, not quadratic, it is simple expression. From there ASC you can get it, this is a value. So that much reinforcement is required. Longitudinal reinforcement need to be provided in the column. So provide 620 mm diameter of bar and 216 mm diameter of bar, which will give you 2287 square millimeter square area. So we have to provide 2238. We have provided 2287 millimeter square area, where six number of 20 mm bar and 2 number of 16 mm bars are provided. And now if you compute what is the percentage of steel you provided, this comes out to be this area to, 2287 divided by b into d, right? So that will give you percentage of steel, how much it is, that is 0.953, which is minimum is 0.8, right? So it is more than minimum, and less than is maximum is 4, we have to allow. So 0.8, it is more than 0.8 and less than 4, right? So hence it's fine. So whatever reinforcement we provided, p equal to 0.95%, and that is fine. So step 3 is also over. Now in step 4 we have to find it out the last step, that is the lateral ties, right? So tie, now the transverse reinforcement you have to find it out. So where we'll get it? So in this clause, if you visit clause number 26.5.3.2 C2, so here it is mentioned that the diameter of the transverse reinforcement shall not be less than 5 by 4. What is 5? 5 is the dimension of the longitudinal bar. So longitudinal bar we provided 20 mm, right? 620 mm bar and 2 to 16 mm bar. So pi by 4, 5 by 4 or 6 mm, which one is greater or not less than? Actually minimum we have to provide it. So we have provided maximum, how much, what is the largest largest diameter? We have used longitudinal bar, which is 20, right? So 20 divided by 4, which comes out to be 5. So 5 or 6, 5 or 6, so which one we have to provide? Not less than 6. So the minimum diameter of the bar we will be using 6 mm. Okay, so from this 5 by 4 we got 5 and 6. So out of these two, which one is maximum? That one, they're not less than, right? Which one is maximum? That we have to use it. So here we are using 6 mm as a tie bar. So in tie bar also now we understand. So column, right, and these longitudinal bars are also provided. So what is the longitudinal bar? Here we provided it 6 number of 20 tor bar and 2 number of 16 mm bar, right? So this is the longitudinal bar we provided. Now we have to provide lateral tie also, right? Lateral tie means, so these are the lateral ties. So tie bars dimension we understood, dimension is 6 tor bar we have to provide, a 6 mm diameter bar. Now what will be the spacing of tie? So that we call it pitch, right? Pitch of the lateral tie, you will get it in this clause number IS 456, should not be more than at least the least dimension of the column. So least dimension of the column is 400 given to us. The 16 times the smallest dimension of the longitudinal reinforcement. So smallest dimension of the longitudinal reinforcement is 16 into 16, 256 and 300. So which one is lowest, that actually you have to provide. So 400, 256 and 300. So we can provide 256 or 260, something like that, is the pitch or the distance between two tie. So now this is our final section of design. So we have, our design has completed. So we have provided uh, 620 tor, right? So 1 2 3 4 5 6. So this 620 tor bar, whereas 216 mm bar, something like that. If you see, it's 216 mm bar here and 4 and 620 mm bar, and this tie is basically 60 at the 250 center to center. We have provided it. So and pitch is 250 as we already computed, and this is the final figure for the design. So this section we have to give it to site engineer. He will be executed on site. So that's how we completed the axially loaded short column design. Very simple design. You have to use just only 4 steps here, and the final design is completed. So in the next class, we'll be designing a biaxial or uniaxial bending case, and how to design a column where you have the uniaxial bending and then the biaxial bending.